Hello, everyone. Thank you for joining. My name is Abhi Mupiri. I am the marketing manager for Data Converters Group, specifically DAC product line. And joined with me is our systems engineer, Uttam Sahu, who is the brains behind these products. Today, we're going to talk about Smart DACs and Smart AFEs. They are a new building block with new possibilities. We're going to explore these new possibilities. And most of the folks listening to this session are probably analog engineers. So before I start my session, I want to ask a very simple question. When you design analog circuits, do you feel a need of adding a microcontroller? Or do you feel the need to add, in order to add a simple logic, do you feel the need of adding a microcontroller in your circuits? And in this process, have you ever faced the burden of writing software even though you are not a software engineer or seek the help of a software engineer, and then went through the whole process of maintaining the software, refreshing it, and even maybe perhaps even qualifying it to get it to a release state? Um, if if you had to go through this ordeal just to add like simple logic or programmability in your circuit, then this session is perfect for you. In this session, we'll provide an answer to all these questions on how our new product portfolio, Smart DACs and Smart AFEs, solves the burden of software for simple analog circuit designs. We're going to focus on industrial applications that include block diagrams and circuits of various systems and even subsystems, where our products are able to create predictable, let's say, predictable power up or tunable set points without using microcontrollers in real time. And the best part, as I mentioned to you, is we can add intelligence to your analog circuits without the need for the MCUs. As a preview, as you can see in these circuits over here, some of the example circuits over here are like something like a precision resistor circuit replacement, or replacing 555 timers, or even generating like smart PWMs without the need for MCUs, and even as far as even generating some sort of a algorithmic functional waveforms, and even like any sort of a GPIO triggering. And specifically, we'll also talk about medical alarm applications, especially when when the software fails or whenever there's a power outage condition and such. We'll also quickly cover some sort of a closed loop control systems, especially in industrial systems such as thermoelectric cooling or even like solenoid control type of applications. Um, so basically, one of the main things here, right? Our Smart DAC products have, the way we are able to do this is mainly because we have a lot of functionality built into the part, where we have a built-in non-volatile memory. We even have like a factory programmable state machines and internal ADCs and DACs that enable us to do all these functions. Our goal here, by building this portfolio of products, is to help our analog and software engineers save cost, remove the tiny microcontroller functions wherever it's a burden, and more importantly, expedite the design cycles and improve the overall quality of your designs. So these products come in two categories mainly. One is Smart DACs, another one is Smart AFEs, and we'll explore both of these in detail with the application circuits. In this slide, I want to cover basically, let's look at what are the main key challenges in an industrial system design that an engineer typically faces on a daily basis, right? So there are two types of designs over here. One design is where systems are based on discrete circuits, and these circuits are meant for low cost and optimized design cycles, where there is very specific solution. These are very specific solutions and typically require a very tight specs. So the good news is they're of low cost and optimized design, but on the flip side, they're difficult to program and they need a lot of custom design, analog design expertise. And obviously, when you're having all these discrete components, your overall board area is going to be much bigger, which may not really be optimally the case. The second type of circuits that we typically encounter are MCU-based or microcontroller-based circuits, which are used to manage complexity of different features and different functionalities. They're easier to use just by changing the software. You have all these additional functionalities, but at the same time, if the complexity is not a desired function, let's say if you need a simple control loop situation, or if you just have one or two functions in your system, then it's definitely going to be added complexity, and it also adds high amount of research and development time, and software maintenance and certification qualification definitely takes up a lot of overhead. And we will go through examples of both these type of circuit implementations and see how smart DACs and smart AFEs provide value. So here, let's get into the details. So what we're doing is we're adding the programmability that is desired of discrete circuits, and we're also eliminating the software overhead that may be unnecessary in simpler systems. And this is exactly the problem we're trying to tackle using our smart DACs and smart AFEs, and let's explore a little more. So now, why a smart DAC and smart AFEs, right? As we mentioned, discrete components will create simplicity in a design, but they're not easy to add in terms of the programmability. They're not easy. But then if you take standard conventional DACs, they add programmability and precision in your analog designs, but you cannot use them without the help of an MCU. But again, if you use an MCU, the software can be used for differentiation, but if the software is not creating enough differentiation, especially when you're dealing with simple logic functions, it ends up actually being a burden than a value adder in some of the cases. And so this is where the smart DACs and smart AFEs come in play, where you have this perfect combination of discrete components integrated into our smart DACs, and DACs or ADCs also integrated into the smart DACs, while also having programmability and finite state machines built into the smart DACs and smart AFEs, where you can actually pretty much do all of these together. So in the end, analog design is fun, and we want to make it more fun by adding, by having smart DACs, because adding programmability may not necessarily be fun. And here, let's explore what actually is a smart DAC, and we'll also, in the next slide, we'll also explore what actually is a smart AFE. So when it comes to smart DACs, we know that a DAC means a digital to analog converter, right? And so it has a digital interface, mostly an I2C or an SPI. It has an analog output, which is, in most of the times, it can either be voltage, and in some case, it could be current. Now, to make this DAC an MCU less, and so that it can autonomously operate and create value in analog design, what we did is we added certain additional functionalities, as you can see here. Okay. For example, an NVM and some other functions like comparators, GPIO triggers, and PWMs. And so when let's go over each of these functions really quick. So for example, one of our basic products that we have is a TPL 1401, and we'll explore this product a little more in detail. It has a built-in NVM. This functionality will, what it does is it creates value by having this autonomous capability of adding programmable current limits and also replacing precision registers, etc. And similarly, we added GPIO control over here. And what it does is a product like 53701, another kind of a smart DAC here, is what we can do is we can now trigger the output or change the output without using the I2C or SPI. So you can kind of pretty much get rid of the MCU and just use a GPI based trigger to pretty much control, and you can use it as a latching comparator or any sort of a programmable comparator. And we'll also explore these circuits in detail. Similarly, we have provided like a 4 series output where we expose the feedback pin of the output over here. If we expose the feedback pin of the output without using the I2C or SPI, so you got rid of the MCU control, and you have this device for any sort of fault managing or an LED kind of dimming kind of a circuitry. Okay, and so similarly, we provided let's say we added a triangular waveform generation into the VFB pin, or by setting the VFB pin, like for example, in this case, we have a temperature sensor, and by setting the VFB pin at a certain level of voltage or certain level of sensing voltage, you can kind of pretty much control the pulse width of the PWM itself. And we also have medical alarm based applications where we can have a combination of smart DACs to perform a certain type of an alarm function adhering to the medical standards. And we'll explore more into this detail. And shown over here is the high Z state especially used in cases where, like, when you have power supply margining, we need to scale the voltage of the ASICs or FPGAs. When the device is off, we have provided this high Z functionality um, even when the VDD of the device is off. And this enables the DACs to use the power supply sequencing so that you can have a hassle-free voltage margining approach here. And this is especially useful in optical communications and optical networks and such applications. We'll explore more into details, but mainly we want to cover here what are some of the major functions that we're tackling in industrial space using the Smart DACs. And another function here is the hassle-free voltage margin that I mentioned earlier. And Smart AFEs, right? So what is the difference, right, between Smart DACs and Smart AFEs? Is this main two additional, these two additional blocks over here. Basically, what we have is we have both the sensing and the control element without having the need for the software. In this case, we've added an ADC and also state machine controls where we have that integrated approach. And with this Smart AFE, you can pretty much do any logarithmic fade-in, fade-out type of waveform generations, or you can also create an analog to PWM conversions. You can create closed loops with lookup tables, or some sort of if this then that kind of controls. You can have cascaded animations, lighting applications, and such. So there are so many different applications, as you can see here. Logarithmic fade-in, fade-outs, analog to PWM conversions, where you have like an analog input and create like multiple PWM outputs, where you're actually using both the ADC and the DAC functionality inside the part, and you're actually maximizing the amount of state machine controls by having if this then that controls, or having multi-slope thermal feedback or single-slope thermal feedback in industrial and automotive applications. Also, like cascaded animations, where you have these industrial lighting or home lighting or building automation type of controls onto the LED lights. We'll explore more into these details, but basically we want to add the main reason. So again, just to touch base as a summary, right? What do we have, right? The advantage that we have, the value that we add is that for a hardware engineer, the biggest value adder is that we're adding programmability without the need for software. And on top of that, for a software engineer, the biggest delight here is that they're able to have a chance to simplify their software on a typical MCUs by kind of offloading or by removing the software dependence in a hardware controlled environment. And more importantly, for a program manager, you're actually reducing the R&D cost and the overall product cost, and effectively reducing the overall design cycles while improving the efficiency in the system design. So without any ado, let's get to an example here. So shown over here is one of the basic Smart DACs, as I briefly mentioned before, is a TPL1401. It has an internal reference with 1% accuracy and also a programmable non-volatile memory, as you see over here. And another important feature of this device is that this device can be set to high Z upon power up, or has a programmable startup using whatever you configure onto the NVMs. And it also has a lock bit to protect any sort of an accidental writes and or accidental writes or reads to the writes to register or to the NVM settings. You can configure that the NVM settings using the I2C, and once you configure it, you pretty much don't need to worry about it. So typically, let's say in some sort of a factory environment where you configure it, and then throughout the usage of this device, there's no need for any additional programmability. And this is a huge feature when it comes to a lot of industrial circuit breaker kind of applications and such. And we'll explore more in detail. So here's an example where we are generating a DC set point, right? And for a typical DC set point circuits, you need passive components. Like in this case, precision resistors are often used to trim a certain voltage, or maintaining the accuracy of a precision resistor divided across millions of units can be kind of a challenge, right? I mean, that's kind of a manufacturing challenge for a lot of precision resistor manufacturers. And as you kind of increase the precision of a resistor, you're also increasing the overall cost, right? And so another approach is to use using a low-cost buffered digital potentiometer. In this case, what we're going to show is the TPL1401, where you can pretty much use a buffered digipot, but then what it does is it can improve the overall production yield while reducing the part-to-part variation that you typically find in a resistor. And these illustrated applications that you see in the left traditionally like a precision like a resistor divider for a given output, or but a small digipart, or even like some sort of an additional like load regulation circuitry, or laser trimming circuitry, or shunt regulator circuitry, right? Most of these devices face challenges of having that high amount of accuracy across the temperature range. And in this, to solve this, we are using the TPL 1401, where the where you have we've designed it for general purpose applications to cover these various end equipments, where some of the most common applications are setting these programmable limits, or power supplies, or offset and gain trimming in precision circuits. And in this example, right, we can go show an example here. In this example, we can show an example where a TPL is driving the gate of a MOSFET with some sort of a DC value setting, allowing the current to flow from the VCC to the ground through an LED. And using this feedback, one can adjust pretty much the overall buffer digipart output to change the overall LED intensity or the brightness. This showcases the DAC's ability to adjust the output and provide a controlled fixed DC set point or bias voltage for to set the overall proper LED intensity. And this is just an example. So you can pretty much use any sort of precision resistor divider, or any sort of resistance, or any industrial need where you have this buffer plus a precision resistors. You can pretty much use that circuitry and replace that by using a TPL 1401. And another example here is an adjustable current limit. So in this case, it's kind of similar to the previous case where replacing precision resistors. But in this case, let's say let's take the example of an LED driver or a DC-DC converter where you need that precision resistor, or an EFUSE or a high side switch where you still need that precision resistor, or an amplifier, power circuitry, or a standalone battery charger circuitry where you kind of need that the precise amount of resistance divider. And in any of these situations, right, we can pretty much use a Smart DAC by setting these programmable current limits in a system, with the DAC driving. In this case, let's say in this example, we have a standard digipart where you have, in this case, you have with the built-in NVM, where you can pretty much drive the IE-ADJ pin over here, and then you can control the LED driver, and the LED driver can then drive based on the varying current through the LED. The LED current can be set accordingly. And the DAC can use its internal feedback network to make sure that its output is well within that derived, well within that range. And the biggest differentiation here is the integrated reference that we provide, and also the EEPROM. And the best part is the EEPROM has over 40 years of usable life at 125 degrees C. And pretty much all of our Smart DACs and Smart AFEs are AEC Q100 qualified, which makes it ideal for a lot of automotive and core industrial applications. And being able to support the memory retention for 40 years or so, with as high temperature as 125 degrees C, makes them ideal for any of the robust industrial applications. And also, not to forget, this integrated reference, providing the additional less than 1% accuracy, is also a very neat feature for industrial designs.
Abhi, I want to just pitch in here.
Yes.
So in these two applications, what Abhi pointed out, the DC set point or adjustable current limit, and we're also going to show another application. We can pretty much use a standard digipart as well. But the problem with the standard digipart is that it doesn't come with a reference. So you need to use an external reference. And by itself, if you are using the digipart in a rheostat mode, as we have shown here, you actually need a very good accuracy of the digipart. And if you look at low-cost standard digiparts, they come with 20% end-to-end tolerance. And higher accuracy digiparts, of course, are expensive. What TPL 1401 provides is the integrated reference, as Avi pointed out, which is providing 1% accuracy. So you don't need an external reference, and at the same time you got the accuracy that is required. And it is also available at a much lesser cost as compared to a standard digipot with 1% end-to-end accuracy. So that's the advantage that TPL 1401 provides here.
Thank you, Uttam. Makes sense. And you get all these additional accuracy and all these additional feature set at the lower cost. And we have several examples where we're replacing precision resistors at a lower cost than a typical precision resistor. So that's the big advantage too. You get all these additional features, but also at a really low cost. Another example is the laser diode analog power control. And in this circuit, as you can see here, you have a resistor divider circuit that's pretty much along with the buffer, pretty much providing typically you can achieve an analog power control by having this resistor divider or having some sort of a standard digipot. Like Uttam mentioned, the standard digipots are expensive when you kind of increase that overall the accuracy that you're kind of trying to achieve. So what we do is by using the TPL 1401, not only that you're achieving lower cost, but you are achieving three main benefits. One is you have that factory programmability. Being able to program it at the factory eliminates the overall runtime programming during the operation of the device. And you also have a simple way to actually accurately generate the bias. And this, what it does is this accuracy, this ability to actually accurately bias the laser is a huge additional benefit. And along with that, you can also offload kind of like most of this to other components. For example, the high-speed modulation DAC need not take the load of controlling this bias dynamically. And that's a big feature as well. And these are the things that you typically may not be able to achieve using a precision resistor divider or a standard digipot. And so that's kind of the huge differentiation aspect of the TPL 1401. And here's another example of Smart DAC, DAC 53701. We have an automotive grade version, also at a low cost. And here, it has one of the main additional feature that this device has. It has a GPIO configurable upon power down. It also has a PWM input, functional triggers or fade in, fade out triggers. And it also has a user, as always, it also has a user programmable non-volatile memory. The PWM output is possible to generate a free running triangular waveform in the VFB pin over here. And it also has I2C interface, and it comes with a 2x2 package. Let's explore a few more use cases of this particular DAC 53701 product. One of the major appliances, right? So for example, appliances such as, like toaster ovens or microwave ovens or refrigerators, or even like cloth dryers, right? They implement door lighting for monitoring the status of an appliance function. These door lights usually dim or brighten for a certain time frame when the door opens or closes, right? And appliance manufacturers prefer to provide a smooth dimming or brightening transition for a better user experience. However, when you use a microcontroller, which is typically the case, right? You need to implement a separate exclusive microcontroller with an additional software, which is usually a huge overhead, especially in a heavily commoditized appliance market. And for this reason, for high-end applications and low-end applications, we have this DAC 53701. It provides an easy-to-implement way, and also, more importantly, a low-cost way to control the slew of such lighting without the need for software. And in this case, shown over here are two different examples of where a smart DAC is driving an LED or actually controlling the bias of an LED. Where the best part is the manufacturer can implement this scheme and program the NVM once and for all, and they're good to go. A very similar approach of controlling the slew, up or down, brightening or dimming, can be taken to various other lighting applications as well, where the smart DACs can pretty much drive LEDs where they can act as a fade in, fade out signal generator, which just using a simple GPIO triggering. And we also have a separate app note that actually covers this that we'll be releasing in the ti.com. Here's another example of voltage margining and scaling, especially for power supply margining, where you need to scale the voltage of ASICs or FPGAs, especially when the device is off. We have provided this high Z output, where you can pretty much have this high Z output even when the DAC is off. This enables the use of the DAC without the use of any power supply sequencing, so you can get this hassle-free voltage margining using Smart DACs, especially a product like 53701. We've seen this circuit being used in especially optical line cards and modules, rack servers, Ethernet switches, and routers. It's very important. It's very critical for these applications to have this high Z output, and we solve that problem by using our Smart DACs. And any overshoot, as you can see over here, the V out is prevented, and as a result, a smooth power supply margining and scaling can be used. And this can be applicable, especially when you have multiple subsystems within a system where you want to provide that SMPS margining circuit. Anything that you would like to add here, Uttam?
Yeah, one of the key features this DAC provides, apart from just being a margining DAC like any other DAC, is the option to kind of take the output to a safe state by using a GPI. Now consider a brownout condition in the system, and the brownout is detected by a voltage supervisor. In a normal scenario, you take the brownout to an MCU as an interrupt, and the MCU considers that as a high priority preemptive interrupt, and it generates another I2C right to the DAC to take this SMPS output to the nominal condition. In case there is a crash in the software, or suppose the MCU is not able to respond in time, the SMPS will be running at probably an elevated voltage, as if everything is normal. What we are providing here is that you can eliminate this I2C write and the need for MCU to be the intermediary. You can directly connect this voltage supervisor output to the GPI, and you can configure the GPI to take the DAC output to a programmable value which is safe for the system. So that is how it kind of adds these simple functions to make the life of the designer kind of easier. That's the advantage the Smart DACs provide as compared to the normal DAC functions. Yeah.
Thank you, Uttam. Makes sense. Here's another example, especially in appliances or medical devices or some sort of an automation or industrial applications. The Smart DAC can act as a programmable comparator, which provides programmable hysteresis and output latching function. This can simplify a lot of fault management software. It can pretty much reduce a lot of overhead of using that software, while also reducing the overall board size. And this figure shows the programmable hysteresis and latching comparators, and how the DAC output can be tracked within a threshold set by margin high and margin low values, which can be stored inside the built-in non-volatile memory. In case of programmable hysteresis, if the value exceeds the margin high value, then the GPI will toggle low. If the track voltage continues to drop below a margin high, then no change will occur on the GPI until the value drops below the margin low value, which will cause the GPI to trigger high again. And this is very useful when you want to raise an alarm when a given value exceeds a threshold, or when a set of data only needs to be within a recorded value, within a finite set of recorded values. And in case of a latching comparator, all you need to do is set the margin high to a full scale code and the margin low to zero, and the GPIO will, once it goes low, it will never toggle after, no matter what the DAC data looks like. And these are, like, some of the very core industrial applications. And this, again, I want to highlight the importance of having this EEPROM, right? Once you have this programmable within the EEPROM, you have this high amount of 40 years of memory retention, and this makes it very much suitable to pretty much eliminate some of these usually typically MCU based software or firmware functions into be actually transitioned into smart DACs. And the best part is you're achieving that at the lower cost and also a smaller size, and you can do it, you can program this once during the factory assembly process and call it good.
I want to add a few points here. All analog engineers at certain point deal with comparators, and whenever you talk about comparators, you have to add some amount of hysteresis for noise immunity. But what's more important is that as you put that comparator into different designs, you need to keep changing the hysteresis value. And in a standard application where you put registers in a Schmitt triggered circuit using op-amps, the hysteresis is mainly provided by the registers, and now you need to go and change those registers to program different hysteresis. So what's the way out? The way out simply seems like you have to change those registers by digipots, which looks much more complicated. Here, what we are providing is a programmable hysteresis option by putting additional 8-bit registers, 2 of them, and you can program your hysteresis value here. These kind of functionalities you also find in some precision ADCs, but the difference here you see is that ADCs typically provide up to 4 bits of hysteresis, while these smart DACs provide 8 bits of hysteresis independently. So your margin high is an 8-bit register, your margin low is an 8-bit register, and now you can store these values in an EEPROM. That means you don't need to program these values every time at power up. You can program it once at production, and after that you don't need any connectivity to the I2C pins by freeing up your I2C bus and the MCU resource.
Perfect.
Please go ahead.
Yeah. Here's another example of using smart DACs, especially in like patient monitoring systems that are used in ICUs. Smart DACs can generate a secondary or a backup alarm function, which provides some sort of a pre-configured patterns, as you can see over here in the bottom right side. And based on that, the GPIO-based trigger will actually provide these, especially when the system gets hung up. And the best part is, these can ease up the overall regulatory approval of eliminating the need for the software. As seen here, some of the IEC standards are covered across the requirements for pulse and pulse envelopes, and and also the overall burst specifications that are being specified. And our smart DACs, one of our smart DACs here, in this case it's DAC 53701 and also the DAC 53401. They can generate all alarm burst tones for all alarm priorities, thereby meeting the frequency range requirement and also complying with the harmonic specifications of the alarms. All medical devices, typically that implement the smart alarm, using the smart DACs comply to a standard. In this case, it's IEC 60601-1-8 standard for medical alarms. And then the figure on the top left shows how the software functionality can be offloaded to the DAC 53701 to generate the medical alarm in a cost-effective and in a more time-efficient way to avoid software development cost and the time frame. Figures. Yes.
Yeah, I can add a few points here. So, based on our discussions with various customers, the key question that we keep getting is that we already have some alarm implementation in the system. Why do we need to switch to this kind of implementation? So there are two main aspects to it. One is this standard has now been mandated in the medical standard, so you cannot avoid by using a simple alarm pattern. And the alarm pattern, as Abhi mentioned, is complex. So people usually revert to software implementations with audio files. Now, when you use audio files, you need to have a processor which with an audio engine and then an audio DAC with a speaker to play out that file. That might be suitable in some systems with an ASIC or a processor, and you kind of put an audio file. The problem is the moment you put a critical function like an alarm into the software, now the software becomes a critical component of that system, and it may be the application software. Imagine a situation you are running Linux on a processor, and everything else it is handling is the graphical user interface or simple user interface functions which are not critical by nature. But now just by adding the alarm to that software, you have made that entire software a critical part of the device. So you have to go through the certification of that software. Every time you make a change, you need to recertify just because you have implemented this alarm through audio files. Consider another scenario where you are implementing this in hardware or with another MCU, and every time you need to go and certify this in a test lab, you are going and changing software and playing out these audio patterns in a simple MCU, which is very tricky. So what we are providing here is that we are providing the pre-configured patterns. So you don't need to program the patterns itself, but you have the options to configure the timings as per your need to differentiate between one type of device to another type of device. It kind of offloads the alarm functionality from the application software, so your application software is now non-critical. At the same time, the same circuit now can go into multiple components, because what we have tried to do is not integrate everything. We haven't integrated the audio amplifier or the combination of the pattern creation. So what you have the option of mixing and matching the audio amplifier and speaker based on your industrial design of the medical equipment, and your core part, the alarm generation, doesn't change. So that's the advantage it provides as compared to the integrated buzzer type of products. And you can use the same alarm circuit in primary alarm applications and also in secondary applications for either a system failure or power failure. And because of this GPI-based trigger, now you don't need an MCU to trigger this alarm. You can still play out those configured patterns just by a GPI trigger. So that's a lot of benefits this simple circuit provides just to make the life of the designer simpler.
Awesome. So for additional information, right? So Uttam has written a 2-part blog series and a technical article. If you want to go on a step-by-step journey of understanding and also implementing it in your system, we actually can provide you the link over here. And we are starting to see a lot of success in multi-parameter patient monitoring systems and infusion pumps for medical alarm applications. Shown over here, especially smart DACs that are used for long distance control and fault management in automotive and industrial applications that require a PWM generation. And this PWM in this case is an analog to PWM conversion. And in this case, we are showing an NTC, a temperature sensing circuit, to a PWM generating circuit. Typically, in this case, a smart DAC can act like a PWM generator with a built-in configurable analog to PWM with some sort of a duty cycle translation. The GPI to PWM conversion is also possible. Usually, typically, unlike MCUs, they require or some sort of a timer-based solutions. They consume a lot of R&D cost and also time, and would require additional digital components that are prone to temperature drift. And smart DACs provide this one-chip, low-cost, easy-to-use solution. Shown in this figure, right, you see the DAC 53701 is obtaining the feedback from the NTC thermistor, which is kind of inversely changing its resistance based on the temperature change of the device in its vicinity. And as the temperature decreases, the resistance increases, and the voltage drop over here increases across the thermistor, and so does the feedback to the inverting terminal of the internal op-amp over here. And the output buffer or the output buffer of the DAC, in doing so, what's happening is the smart DAC can change the output pulse width of the PWM output as the conditions of the device, based on the condition of the device that's being monitored over here using that NTC. And the graph here shows how the VFB pin of VFB, the feedback voltage, increases over time to produce a duty cycle at the PWM output. And the direct relationship is that the PWM duty cycle is proportional to the NTC resistance value. And the frequency of the PWM signal is set by the frequency of the sawtooth or a triangle wave that's generated by the DAC. We actually have more information on this in pretty much a lot of our smart DAC data sheets. One of the examples could be in the DAC 53701 automotive version. We actually have implemented the details of this device.
One additional point I want to make here, Avi, is that of course it looks like a DAC here, but let's consider this as a simple way to implement an ADC. Consider scenarios where you have to monitor some analog signal, either it's a voltage or current or a temperature.
Yeah.
And you want a very simple way or not very high accurate way of conveying that data over a simple interface. Now, whenever we talk about analog to digital, we always think about ADCs, but here the digital interface is also can be considered as a PWM, because you can read the duty cycle of the PWM using an MCU. Now, where does it benefit? One is it makes the system implementation simpler. You don't need a complex ADC. And the interface is now a single wire, like an MCU. It doesn't need to implement anything like a one wire or something. So it saves the MCU's resources and pins. More specifically so, when you have to pass this information over isolation barriers, so the cost of the isolators depend on the number of pins they provide. So now instead of having a 2-pin I2C or a 3-pin SPI, you can pass this information just by a single pin PWM. So that's how you solve the problem of the isolator cost. And at the same time, suppose you are using the same approach, but using a 555 timer to generate this. As Abhi mentioned, there are all these drift issues with the external discrete RC component. At the same time, if you have to tweak something on the frequency or the range of the analog signal, you can do that with the smart DACs using software. For timers or any other discrete circuit, you have to touch the hardware, which might be costly, not in terms of just money, but in terms of time, in terms of testing or regulatory approvals. So here you can just use a simple software to tweak the parameters. At the same time, you reduce the interface cost.
It's a fantastic point, Uttam. Makes sense. Absolutely.
Yeah.
Cost and the time. Yeah. And here's another example where, depending on the combination of, the number of modules that you use in the system. In this case, for fault communication between one module to other module, you can pretty much produce a varying PWM cycles, duty cycles based on the type of faults that we can detect. The circuit is very similar to the previous circuit, except that, like in core industrial applications where you want to, where you kind of need the redundancy and the fault detection within a subsystem or in a system between modules, you can detect multiple faults, and that can be communicated across different modules. And Uttam will cover a little more into detail here.
Yeah, so what happens is you think of any system where you need to detect the fault, and you need to communicate that fault to another system, which is like a master or it's monitoring kind of other systems. You can always use an interface like UART or any other standard interface. But if you are concerned about cost, PWM is the simplest interface that you can use. It doesn't lose so much of information over long distance. At the same time, it's easy to implement both on the transmitter and the receiver. What we are showing here is how to convert GPIOs to a PWM signal. So as we talked about the analog to PWM conversion, here if we modify the analog circuit by adding GPIOs as a superposition, and based on the GPIO states, you generate an analog voltage using superposition. The same analog voltage now you can communicate using PWM. So for two GPIOs, you get 4 PWMs, and if we have separate good kind of distance between these duty cycles, the error margin is also kind of good, and you don't need to worry about a loss of signal or kind of bit error rate while transmitting. So that's what this circuit kind of implements, a simple way to communicate the status without any complex implementation.
Perfect. And with that, we'll talk about another device, another Smart DAC, DAC 63004. It's an ultra low power 12 or a 10-bit option we provide for DACs. It has it has a lot of features. For example, this DAC can be implemented in some sort of a subsystem, such as land mobile radios, where we can actually not only adhere to the lower power needs, but the best part is it has multiple channel inputs that can be used for various functional needs, low power functional needs within a system. A lot of battery operated medical devices also are interested in this type of a part. So our goal here was to show that it's not just one or two parts. We are actually releasing a family of parts that cover Smart DACs.
One thing to note here is that this device is the lowest part buffer DAC in the industry in this class, and it also operates at 1.8 volts. So that means not only the current, that is 50 microamps of current per channel, but also at a lower voltage, the total power consumption is less than 50% to the closest competition. So you get the lowest power DAC, 4-channel DAC in this device for all your battery operated applications.
Perfect. So with this, we'll close what we've had to cover for the Smart DACs, and we're transitioning into the Smart AFEs. And here's this slide, we are showing an example of Smart AFE. In this particular case, it's a quad channel. It's a 4-channel configurable DAC and ADCs at the same time. You can pretty much configure any of these DACs as ADCs and vice versa. And it also has a control logic that can have a lookup table based control from any sort of a DAC to an ADC. At the same time, as always, it comes with a non-volatile memory. That means it will store all the configurations, and you can pretty much program with the factory and can operate without the need for the MCU. It has the GPIO interface, so you don't need an I2C or an SPI during the runtime operation of the device or the system. And it also has a PWM output, which is suitable for driving LED drivers, and the 10-bit ADC and the control logic is pretty much used to create some sort of an autonomous control system, thereby making it an analog front end. So one of the examples here is that we use in a lot of core industrial applications is the thermoelectric cooling. For folks who are new to this concept, it's basically thermoelectric cooling is using a Peltier effect, where you pretty much create heat flux at the junction when you have like two different types of materials, and these two sides, when you apply a specific sort of a DC electric current flowing through the device, it brings heat on one end to the other, so that one side gets cooler while the other side gets hotter. The hot side is typically in an application, it's attached to a heat sink, so it remains at an ambient temperature, while the cool side goes below the room temperature. And this is especially useful in a lot of consumer applications, such as portable coolers or electronic component cooling systems, or climate control jackets and such that you find with the mountain climbers and stuff. And also in industrial and automotive applications, such as laser equipments or thermoelectric air conditioners or coolers, mini refrigerators, telecommunications, and also a lot of military cabinets or IT enclosures, where you kind of need that critical amount of temperature to be maintained. And the best part is you can achieve that with much lower board space by using our AFE. And Uttam will walk you through the exact implementation level details.
What the Smart AFE does here is implement a proportional integral closed loop control. And as Abhi mentioned in the last slide, one of the analog channels is used as an ADC, and you monitor the NTC, and in turn you monitor the temperature of the thermal load, and you take that as the sensing input. You put the set point as the temperature to be maintained, the cooling temperature to be maintained, and you can program the proportional and integral gain, and thereby create a feedback control loop. The output can be either analog or PWM, so that you can drive either a class D amplifier or a H bridge and control the current through the TEC. At the same time, you can use another channel as an ADC or a comparator to have a cutoff or kind of saturation of this PWM or analog output by monitoring the current flowing through the TEC in case there is a fault or short circuit there. So that way, what we are providing here is a way of maintaining temperature control of the TEC without loading a microcontroller software, and at the same time you can use multiple TECs of different current ratings just by changing the H bridge or the class D. So your core implementation remains same, and we have made the other part, the high power and high temperature part, modular, so that whenever you change from one system to another, you don't need to touch the core system.
Perfect. And a typical implementation of a TEC is usually done either in a discrete way, or using a combination of a buck boost and a microcontroller, or also there are these new generation of parts that have that actually have this TEC control built into the device, but they use either external MOSFETs, which typically the overall solution consumes a lot of size, or some of these devices have a built-in MOSFETs and the TEC control built in. But the biggest differentiation is that we're able to provide all of this at the lowest cost standpoint. The cost is a big differentiator here, along with providing all this additional functionality of having the programmability and having the built-in ADC and the DACs. providing that feedback loop of temperature control and the current monitoring or cutoff to the valve. The next application in industrial, core industrials, is solenoid valve control. For folks who are just getting introduced to this, a solenoid valve is an electrically controlled valve, and the valve features a solenoid, which is typically an electrical coil with a movable, some sort of a ferromagnetic core. It's typically called plunger in the industry, and it's actually located in the center. And in the rest position, what happens is the plunger closes off a small orifice, and when an electrical current through the coil generates a magnetic field, the magnetic field then exerts an upward force onto that plunger or that electromagnetic core, thereby opening the orifice. This is pretty much like a basic principle that's used to open and close solenoid valves. Typically, refrigeration systems use solenoid valves to reverse the flow of the refrigerants. There's a lot of industrial irrigation systems that use solenoid valves to automate the control of the flow. Dishwashers and washing machines are also good examples where they use these solenoid valves to control the flow of the water. Air conditioning systems, medical equipment, dental equipment also use solenoid valve controls. Water tanks are also a good example. So there's a lot of ranging from as huge as car washes to industrial cleaning equipments to as small, really tiny applications that use the solenoid valve principle. And Uttam will walk you through the value that one of our AFE devices brings to this application.
In addition to what we spoke in the TEC control, that is a closed loop proportional integral control, solenoid valves need something called as peak and hold control. That means before the system goes to the closed loop control, it needs to kind of hold a peak value of the current or the PWM duty cycle for that matter for a certain amount of time. Now this peak value initially does an enhanced slew for the solenoid valve, thereby reducing the transition time. Here, what we are providing here is a programmable duty cycle for the peak value and a programmable time value for the peak duration. And after that, the system goes into the proportional integral control mode, where it senses the current through the ADC and provides a PWM output. And then we can feed it to a MOSFET driver, for example, a DRV 8714 or something similar, which can drive these MOSFETs and provide additional diagnostic features. So what we are adding here, or the advantage of this Smart DAC, is now the MCU doesn't need to be involved in a real-time control of the solenoid valve. All it needs to do is to provide a start and stop command to the Smart AFE, and the Smart AFE then takes care of the solenoid valve control. Now you might have also explored some solenoid valve drivers which are completely integrated. Why not use them, and why to use this combination of Smart AFE and the DRV or the solenoid driver? So the answer is same. You have to, if you keep the core of the part separate from the variable parts, these are called end-to-end principles in software design typically, that you keep the core constant, so the control loop is constant, and based on your solenoid valve, you change the driver so that your driver doesn't need to be having everything integrated. So that way you are separating out the components and making it more modular, and then creating design changes at variants becomes much easier without having to go through the design cycle from the scratch. So the core part implemented by the Smart AFE and you choose the MOSFET driver based on the solenoid you have. And the Smart AFE then takes away the load of the MCU. So your software is independent of this real-time control. So we are providing modularity, low cost, no software burden, at the same time design flexibility.
Perfect. This is one of the last slides we have in this presentation. Uttam, would you like to cover really quick as we conclude?
Yeah, sure. So this is a simple application of the Smart AFE, and we spoke about closed loop controls and all other kind of high-end application. And here we are showing another type of application which is very simple, which is non-obvious, so we don't see it in real life. But these are this is gaining traction with many of our customers. So most of the times we have the need of I/O expanders in systems. And whenever we talk of I/O expanders, we either talk about a digital interface to I/Os, like an I2C I/O expander or an SPI I/O expander. But we take for granted that these interfaces or these buses are free in the system. It's only the GPIOs which are not free, which is not always true. You always have limitations on either the I2C bus addresses or the GPIOs on SPI pins, or whenever you want to communicate something from one type of one module to another module, which are kind of separated by a long distance. That time, instead of going into complicated interfaces or procuring an MCU with multiple GPIO options, we can convert a simple PWM into GPIOs by using this device. So you take the PWM input, and based on the value of the duty cycle, we can convert that into 4 GPOs, general purpose outputs, using a lookup table which is programmable in the EEPROM. So that way you can actually make a very simple and low-cost solution for your I/O limitation.
Perfect. Thank you, Uttam. So yeah, this concludes the overall session, and we want to let you know and highlight that Smart DACs are out on TI.com, and Smart AFE products will also be releasing shortly. We are very excited. You'll see this first set of Smart AFEs released by the middle to end of March this year, 2021. And so yeah, we would like you guys to explore the Smart DAC and Smart AFE page on TA.com, and also all of its associated in-depth technical collateral that we're issuing. We are having a lot of cookbook circuits, application notes, technical articles, and also a lot of blogs that kind of like showcase the introductory level of a system design. With that being said, we would like to thank you for joining this session, and please send us your questions that you might have as a follow-up to our emails. The main points of contact here, as you saw, was Uttam Kumar Sahu. He's our systems engineer who just spoke in this session, and Gavin Bakshi is our product marketing engineer, and this is me, Abhi Mupiri. I'm the marketing manager for the DAC products. Thank you for your time, and thank you.
Thank you, everyone.